Hello all, today we're going to be looking at such a powerful rule that's actually called the power rule. We're going to be learning how to differentiate terms that are generally found within polynomials, and it's going to be a lot of fun. So, it's almost time for us to get started, and by the end of today you'll be able to differentiate a lot of polynomials. Okay. So you remember from first principles, the equation that we had, that we're able to find the slope of the tangent, or an equation that helps us find the slope at any given point. Well, that's all fine and dandy, but it's quite a long process. It's quite tiresome. And the fact of the matter is, there's a lot of other patterns we can use to make this a lot simpler for us. And that's where the power rule comes into play. So many mathematicians over the years have actually gone through and used a few different differentiation techniques and actually found what happens when we try to differentiate a term like x squared, or x to the 3, or 5x to the 7. So, what they found was that if you wanted to find the derivative of, say, x to the n, where n is just a number, then the derivative of x to the n is just a matter of bringing this exponent out the front, down to there, so we have nx to the n minus 1, because we need to subtract 1 from the exponent. If you continue doing calculus and go on to integral calculus and actually have a look at this, then you'll understand why this is the case. But when you think about it, the main way you can actually tell whether a function is differentiated correctly is that the maximum power, or the highest order, should be decreased by 1. And you can go ahead and you can use first principles, that fancy slope equation that I actually showed in the second video of this season, and you will get the same results as actually doing this process. Again, lots of mathematicians before you have actually gone through and done the tedious work, so your job is a lot easier. So, let's have a go at differentiating x squared. This actually says, well, what's the slope function for the function x squared? So x squared is our f of x, and we want to find our f prime of x. And then we might want to find the slope when x equals 2. Again, there are many reasons why we might want to find the slope. You may remember from my first video, we were driving down Calculus Highway and we wanted to work out how fast we were going. Or we wanted to know how many little bacteria were added to our colony plate every hour after the third hour, as a rate of change. Well, it's simple. We bring this power down and multiply it by the coefficient. The coefficient in this case is 1, and anything times by 1 is itself. Then we just have x, and we subtract 1 from the power. 2 take 1 is equal to 1. So our answer is just 2x. And when you think about it, does this make sense? It's always good to assess your answers and think, well, is this logical, or am I completely off? Let's think about the parabola x squared. We know that it's definitely not linear, and we know that the rate of change is increasing, so it's logical to assume that this may possibly be 2x, because if we were to look at the f prime of 1, it would be 2 times 1, which is 2. But if we were to look at the f prime of 2, that would be 2 times 2, which is 4. And the f prime of 3 would be 2 times 3, which is 6. So the slope gets faster and faster. And you know from a parabola that that's true. The slope does get steeper and steeper. Excellent. So now let's have a go at differentiating something slightly more challenging. Let's have a go at this last one up here. 5x to the 7. What's the rule for that? We have a coefficient out the front this time. Well, it's quite simple again. If we want to find the derivative of a polynomial term where we have a as a coefficient, x as a variable, and n as our actual exponent, or the power to which it is raised, then we can use this version of the power rule. We can bring down the exponent, multiply it by the coefficient, and then subtract 1 from the power on the variable. And it's as simple as that. That helps us find the slope of a function like this. So, let's actually go through and do this. Let's find the derivative of that equation. So we bring down the 7 and multiply it by 5, because that's our coefficient, 7 times 5, and then we subtract 1 from the power. 7 take 1 is 6, and hence we get 35 x to the 6 as being the result of applying the power rule there. Excellent. So we now know how to differentiate polynomial terms. Well, guess what? We can actually take this a step further, and we can actually differentiate terms that are added together, because it's not often we get a function that's just that. We generally have other polynomial terms added on too. Let's have a look at an example of one. Well, let's say that we had a function 2x to the 3 plus 3x to the 2 plus x. And we wanted to differentiate it. Well, guess what? There is a thing called the sum rule, apart from the power rule that we just learnt. And the sum rule says that if these are added or subtracted from each other, then we can actually differentiate each term individually and get an answer for it. And we know how to differentiate these powers because that's in the form of ax to the n. And hence, that means that we can actually differentiate anything that has pluses or negatives in it with basic polynomial terms. So let's give it a go. The f prime of x, which can also be the change in y relative to change in x, that's just alternative notation for the derivative. Again, it's just that slope, that little bit of change, that rate of change. Would equal, we move the exponent down and we multiply it by the coefficient, so we get 6x squared plus 6x and then plus 1. Now you're probably wondering, how did you get the plus 1? And this can technically be 6x to the 1 as well. But what happens here is, this is the same as having x to the 1. Because it's simply just x. If we actually multiply this out the front, it'll be 1 times 1. And then if we subtract 1 from the power, it's going to be x to 0. And you algebra buffs know that anything raised to the power of 0 is just 1. So that's how we get the last little bit there. And that's our derivative. Because we know that simple polynomial rule for differentiating a single polynomial term, if they're added or subtracted, we can go through a whole chain like that. Let's have a go at doing some where some of the terms are actually negative. And let's see what happens. And again, that's just the sum rule. Okay. Our function is going to be equal to 5x to the 4 take 2x to the 3. Our first derivative will hence therefore be 20x to the 3, because I'm taking that 4 down and multiplying it by the 5, and then I'm subtracting 1 from the coefficient, and that's how I get 20x to the 3. I then take that 3 down and multiply it by 2, so I get 6, and then I subtract 1 from the power, so it's 6x squared. It's simple. If you know those few rules and you actually practice them, then you're well on your way to understanding what's going on here. So, just to finish off, I'd like to give a reasonably challenging one. Let's find the derivative of a function which is 5 pi lots of x to the 7 on 2 plus 6x to the 9 on 2. You're probably thinking, wow, that's a lot of fractions, that's a lot of stuff going on. But in the end, it's just simple. And I won't get you to simplify it too much today. It's just about the process that counts. So if we want to find the f prime of x, well, we need to identify a few components. 5 pi is just the same as having an ordinary coefficient out the front. Pi is roughly equal to 3.1415926535, etc. So it's just like having a number out there. And we've dealt with numbers before, like 2 or 3 as a coefficient in the previous examples. So we just treat it as though it's a number. Okay, so we take that 7 over 2 down, so we end up with 7 over 2 times pi on 5. I won't get you to simplify it at the moment. Feel free to, if you have a graphics calculator, simplify that into a decimal approximation if you wish, but you don't have to. And then we have x, and we subtract 1 from the power. Remember, that's the power rule, that powerful rule that we have been looking at. And 7 on 2, take 1, is actually equal to 5 on 2. Hopefully you should be able to see how that works. If you want a little demo on how this works, consider it as being take 1 on 1. In order to subtract fractions, we need them to have the same denominator, so we multiply both of those terms by 2, and hence we get 7 take 2 on that. And therefore we get 5 on 2. And now what we do is we differentiate this last term using the power rule. We bring that little exponent down to the front. So we get 9 on 2, and we times it by 6, because 6 was there before. And again, you can use a calculator if you want to approximate it using decimals. You don't have to, but then you have x, and generally, to avoid confusion, you can just do a little dot for multiplication. That's what I like to do sometimes, if I haven't simplified it down or used decimal approximation. And again, we get 7 on 2, because 9 on 2 take 1 is 7 on 2. So, just to recap, we learnt a few rules during this session today on how to differentiate polynomials. Again, it's a lot quicker than using this process, because I had a whole video just to go through one of those polynomial terms. And here I've been able to differentiate 2 or 5 even in a matter of minutes. So the power rule. The first version of the power rule says if we have x raised to the power of anything, then the derivative of that is going to be nx to the n minus 1. You bring the exponent down, you multiply it by x, and then you subtract 1 from the exponent. It's that simple. Again, mathematicians before you have actually gone through the process and proven that for you. So you don't have to go through that tedious work. There will be occasions where you may need to use first principles, but for this sort of thing, it's much quicker and easier to use this approach. And the f prime of ax to the n, where we have a coefficient of a out the front, is going to be equal to bringing that little exponent down, so we get nax, and then subtracting 1 from the exponent. And lastly, the sum rule dictates that if we have, say, the h prime, so we have like the h of x as our function, but the h prime of the f of x, where f of x is just one of these terms, plus or minus the g of x, where the g of x is just another one of those terms, then if we just find the derivative of both of them individually and add them together or take them together, then we have differentiated successfully. And those are some of the fundamental and basic rules of differential calculus. In the next episode, we're going to be looking at when terms are multiplied and divided with product and quotient rule. I'll see you then.